Okay, thank you very much for introduction and for the organizer for inviting me here. Okay, so I will keep up with the second talk about tilings today, but will be with unequal cells. And this is a joint work with Matteo Novaga and Paolini. Okay, so quick motivational slides. So the running question in the next slides would be, what will be the best way to subdivide the space in with prescribed number of sets, and let me add unequal sets. And I will be stick to the planar geometry, essentially. So you can find this question from a theoretical viewpoint in the realm of discrete geometry and or calculus of variation and geometric analysis, if you're interested in isoperimetric problems, or in the realm of mathematical applications such as crystals and material science or quantum physics. And so the underlined words I will be interested in rephrasing this way. So when I say best, I will think about lowest perimeter sense. And subdividing, I'm thinking of periodic configurations which are tilings, as you just saw. And when I say prescribed, I'm thinking of an area constraint. So it's really an isoperimetric problem. And as we saw, the most important configuration here in the plane is the honeycomb conjecture in the so-called Kelvin problem, which is basically the tiling of a regular hexagons in the plane. Okay, so why unequal cells? Okay, I will say something about physics literature later, but mathematically, if you're interested in this question as if in the stability of these questions, and you would like to know how almost, say, minimal configurations look like, then it's very natural to allow for unequal cells. This is one first motivation. Okay, and brief outline, I will start introducing my isoperimetric problem, so the one we faced, which in a sense is a generalization of the fundamental domain minimal one, and then go through results. So existence, regularity questions, and then classification. So qualitative description and explicit description of minimizers. I will be interested in understanding configurations as well as energy, so isoperimetric profiles. And then if time permits, I will get to some other problems at the end. Okay, so what is a tiling? A tiling, as we said, you have an integer n, and it's a collection of sets, measurable sets, in the plane. I will just stick to the plane, which are given by the repetition of n different sets, EI, which I will call generators. And these are translated copy of those. And the translation is achieved by lattice action, which is a discrete group of translations. So these generators must not overlap as you run the lattice, of course in a measured sense, and they should cover all the space. And to stress the lattice action, I will say that an n-tiling is periodic relative to the lattice G. And a quick remark, so lattice, as we saw, is any element of a lattice is an integer coefficient linear combination of two special vectors, G1 and G2, which are linear independents, and they span essentially a parallelogram with area, which I will call area of G. And according to the previous talk, so if you make the union of all these generators, then you end up with what is called the fundamental domain, which has precisely the same amount of area. Okay, so we attach a notion of classical perimeter, which is naturally the sum now of perimeter of each generator. 1/2 is just a choice. And of course, you can allow multiple different choices as local or non-local ones. I will really stick to the plane and the classical perimeter in this talk. And the definition of isoperimetric tiling would be then an n-tiling T, which is, will be said isoperimetric relative to the lattice G, provided the perimeter of the tiling is less or equal than of the perimeter of any other tiling T prime, which is relative to the same lattice G, and of course you should match areas. So the area of the generators EI prime should match the one of the starting tiling. And I will just say that T is isoperimetric, regardless of the tiling. Essentially, if this property holds for any T prime and for any G prime, which is any other possible lattice, of course, itself with an area constraint. So competitor lattice G prime should have the area equal to the sum of the area of the generators in order to have the correct amount of area to tile. Okay, so the isoperimetric problem would be then essentially the reverse question. So you fix now area vectors, V1 up to Vn, You fix their size, so the whole sum, and you can ask about existence, so whether this isoperimetric tilings configuration do exist, matching the area V1 up to Vn. And of course, it's both relative to the lattice G or in the sense varying also the lattice. You can ask regularity, so qualitative description, at least at the regular level, so how do they look like in the plane, and classification. So this would be the second part. So at least, for instance, with 1 or 2 repeating cells, how these tilings look like out of an isoperimetric condition. And as was mentioned, there is a literature for n equal to 1. Essentially, we are in the domain, in the realm of isoperimetric fundamental domains, and all these references were already mentioned, both in Euclidean or Riemannian settings. But there is also, in the bigger N case, physics literature, this was called bipartite tilings, in this, with minimal interfaces. And essentially what you will be seeing next, it's analytic descriptions of numerical predictions. So in these papers, they were ranking by numerics, essentially some configurations, and try to guess which one would be the optimal ones. And for n equal to 2, we try to give an answer. And of course, a big motivation was also the cluster theory in geometric measure theory, and the so-called K-bubble problem, at least in the methodologies. Of course, the problem is different. Okay, so let's go through results. The first one is about existence. So this was already commented. Just let me state the existence result in my notation. So you fix lattice G, the vectors, V1, Vn, the area, and you minimize the perimeter functional among all these kind of tilings configurations. And in particular, minimize exists and is isoperimetric relative to G in my sense, in the definition that I gave. And of course, you can also minimize among all lattices with prescribed area. And it will be just called, as I said, an isoperimetric N tiling. And of course, here the strategy is, as was said, this direct method, which is complemented by a concentration compactness step. And the reason is that out of boundedness in perimeter, you just have L1 lock compactness, and you will lose eventually the other constraint. So you have to complement standard direct method with a concentration compactness, which basically brings back translating copies and escaping copies of my sets. You restore L1 compactness, and then you hope at the limit to preserve the area constraint so that you really get a competitor at the end, which has the lowest possible energy. And the regularity would be a planar regularity about isoperimetric tilings. So now we fix lattice G, and we consider an isoperimetric N tiling relative to the lattice. And then we can say something about the generator. So for every I, a generator should have an open and bounded representative. This is like the basic a priori regularity results. And I will consider from now on, when I write EI, this representative. So without specifying. And it's regular, I mean, it's a smoothness result. So the generator should have a finite number of connected components, and the topological boundary should be made by a finite number of edges, which are either straight line segments or circular arcs. And it is a classical planar regularity theory. And of course, the edges must meet, we have this local condition with angles of 120 degrees. Okay, so just a quick comment. So this would be really regularity theory for minimal cluster in geometric measure theory. So in planar, this is really the planar regularity theory that you would get out of, for instance, standard tools. The point, as was mentioned, is that this application of regularity machinery is not for free, in the sense that if you look at some ball, how many copies hits the ball, it's not for free that these are finite number. And in particular, you cannot directly apply the regularity theory for cluster minimizers. However, there is this thing is that in dimension 2, it actually turns out to be locally finite, the isoperimetric tiling, and then you can apply this regularity theory. This is just essentially how you bridge towards something that is known. Okay, so now let's go through what I believe is the most interesting part, which is about classification. And the goal here is now to take n equal to 2, so that we can say something more and something new eventually. And we want to classify isoperimetric tilings. So let me start with a remark, in a sense, which gives some intuitions about borderline cases. One is the degenerate case, when you have one generator which is negligible. And in this case, the tiling will be degenerate. And out of regularity theory, you pretty much soon understand that this should be an hexagon, the remaining cell, which of course is not regular, depending on the lattice, and might look like this one. The second one, which actually is a guess, it's the other borderline case where the two generators have the same amount of area. So in this case, another good guess is still this picture, but now the lattice should be rectangular. So we are talking about another lattice. So in this case, the two generators will tile again the plane. And the guess now is that, okay, these are borderline cases, but there should be a whole family in the middle of different situations. And this is what we found out in collaboration also with Emanuele Paolini. So essentially, if you take a non-degenerate, so positive area, isoperimetric two tilings, which are related to a given lattice G, then from regularity theory, we know that these should be curvilinear polygon with the 120 degrees angles. But now we have some information about the structure. So we know that at least one of these following holds up to exchanging the two generators. So the configuration 3-9 would be essentially a hexagon. And then you put at the vertex a small velour triangle, which is like inflating depending on the area. Then we have eventually we can also have a configuration 4-8, which is a strictly convex curvilinear quadrangle, which has this rectangular symmetry. And the E2 would be a chipped polygon octagon, which is chipped to allow this to make room for this object. And the last one would be configuration 6-6. Which two hexagons, which are sharing a flat edge. Of course, all of these would tile the plane according to the lattice, and the lattice here is different, but if you want to visualize the tiling structure, this would be the classification result. Okay, so there is a good remark about this is that in a sense, it's a progress, but it's not completely satisfactory. And there is that if you take lattice G, then this theorem is not saying whether all three configurations are possible. We just know that at least one should be there. For some lattices, we believe that might be just two. For others, all of them. But it does not come with the theorem. And of course, we don't even know the value of the cost. So it's quite implicit in the computation. But remember, there is another notion of isoperimetric tiling we have at disposal, which is about when we further minimize among lattice G. And in a sense, in this problem, there might be hope in order to address also this kind of questions. And the reason is that when you further minimize among lattices, then you might select more symmetric configurations. And then computation hopefully would be way far more accessible. And the last hope, which maybe was a bit implicit, that you would like to understand exactly when you pass from one configuration to another. So what I will call phase transition. Okay, so in order to rephrase all these questions, let me introduce the notion of isoperimetric profile. So now by scaling, essentially, let's look at the area 1 lattice. And an isoperimetric profile function relative to G would be this function Ag of x, and now x varies between 0 and 1. When you minimize the perimeter of a tiling, where you prescribed area x and area 1 minus x. So in a sense, you exchange area between the two as x varies. And then you further minimize among lattices, and this will be called isoperimetric profile function, I of x. So now the goal is to compute I of x, to understand minimal configurations, in a sense, as x varies, minimal lattice structures, and uniqueness of the isoperimetric tilings. And the formal theorem is this, which I will try to convey with pictures. So essentially, I of x is explicit. This is the main point of this theorem, and is piecewise graphical between two explicit points, which I will call phase transition points. So we know the value precisely. It's just approximations. We know exactly the graphs between two successive values, and we know what happens in the middle. And let me try to explain what happens with this plot. You have x-axis, you have area between 0 and 1/2, and then would be reverse picture from 1/2 to 1. We have phase transition point x1, x2, and then we have the value of a of x on the y-axis. And the idea is that you start in the degenerate case with a regular hexagon, and then you start inflating as x increases with the 3-9 configuration, which now looks way more symmetric. It's like a regular hexagon with a chipped with a low triangle on a vertex. So this happens until point x1. At x1, you have the first phase transition where it is essentially equivalent convenient to have this configuration or configuration 4-8, which is now symmetric. It's like a square chipped and a curvilinear square at a vertex. So as soon as you detach from x1, then the hexagon is not more convenient. So this would be the optimal one, and this goes up to x2, where you have the second phase transition. Now it's equally convenient to have also hexagons, which are sharing a flat edge. And from x2 on, essentially, to 1/2, the profile is constant, because you can move the flat edge in order to exchange areas with the fixed perimeter. So this is basically what's written here from 0 up to 5. And the last comment is that unless you are at phase transition points, the tiling is unique up to isometries. So this is the only uniqueness statement that you could get. And if you would like to visualize it, this would be now the symmetric isoperimetric tiling configurations that we found. Okay, so I guess I have few more, 5 minutes, 6 minutes. Okay, so let me mention some overall problems attached to this analysis. The first one would be what happens with the bigger n. And this actually, in the first place, so now if you fix more than 2 sets, repeating sets, this actually was something that we asked in the first place before this explicit analysis, because we were investigating some qualitative, say, stability results that touch the honeycomb. So there is a regime which you can guess it's easier, where all the areas here are almost close to each other. For instance, say almost equal to 1. And you should expect that the honeycomb tiling, suitably perturbed, would be a candidate minimizer for the perimeter functional. So the formal statement, which is qualitative, is the following. So for every n, there exists a delta, which is non-explicit, a parameter between 0 and 1/2, such that the following holds. So for any n poles of area vectors, which are close enough to 1, and they all sum up to n, in a sense, I'm thinking of area of the lattice equal to n, then the cost of an n tiling, which is isoperimetric, matching precisely the area V1 up to Vn, should be this one. So n over 2 perimeter of a regular hexagon. So if you forgot the normalization factor, should be n times the perimeter of a regular hexagon. And there is a good reason why this should be the cost, because this structure now, it's a competitor. So you take n stacked regular hexagon, and then you start perturbing the flat sharing edges, and this to match area. And perimeter is not changing. So you should think that this is a good candidate minimizer, or at least the good cost, should carry the good cost. And this is what I was saying. It's a competitor, and of course the theorem is qualitative, so it goes by contradiction. And the contradiction is quite delicate, but essentially it relies on compactness argument with some a priori regularity that we have in the plane with stability of network. So the stability of the final object, the regular hexagons at the end. Okay, and then a few quick problems. So as I said, in the lattice, in a fixed lattice case, we know a little. So we have, of course, implicit trigonometric relation. So a priori, we could get something numerically. But maybe the problem would be to take a lattice because you like it or you have some interest in it, and then trying to understand all the set of questions. So what kind of, when configuration 4.8, for instance, is admissible, which is the middle one. And we expect that when the lattice is too stretched, then there is no room to make, even to draw this, or even to be isoperimetric. And then, like in the long run, like what is the explicit description? A second one, which is maybe related to the Kelvin problem itself, so the source of motivation. It's about, so we have partitions of the plane, 3 different kinds. So are there local minimizers? In a sense, they minimize in average. So this is not really the function that we are minimizing, but of course, now that we have this, it's a good question to ask whether there are local minimizers in the perimeter. And what is curious is that there might be not. So we can show there exist 2 subsets where this cannot happen because you can cook up a better one, essentially. But we don't know whether in the complement of this interval this should be the case. Okay, so I think this is pretty much it. So I leave the QR code if you want to play with the app of Paolini to see all these minimizers as the area varies. So thank you very much.